Welcome back, everyone. Recall from the previous lectures, we are interested in rational intelligent agents, and this will be our approach to AI in this course. In this lecture, let's examine different aspects related to rational agents, and specifically, agent environment in which the agent evolves, and how this affects our design of intelligent rational agents. So let's dive in. Let's define first what's an agent. An agent is anything that can be viewed as perceiving its environment through sensors and acting upon that environment through actuators. An agent can be represented with this diagram in which we have the environment and the agent. The agent box actually has some sensors in it that sense the environment and gets perceived from the environment. And the agent can have actuators that actually act upon that environment, those generating actions or deciding what to do and generating actions. So the first part here allows the agent actually to sense the word in which it evolves. And the second part actually is about acting upon that word. So this is acting. So in the middle you have a part in which the agent will do what? Will do thinking and deliberating. Here the agent, given what it observed or sensed from the word, it will be thinking, deliberating, or deciding, another term for, or deciding what to do based on what it senses. So in general, you could see that as a cycle for the agent in which it perceives the environment, decide, think what to do, act, and so on and so forth. So we have a kind of a loop or cycle happening here of perception, thinking, and acting upon that environment. The last aspect to mention about agent is that they are actually made up of two main components, and these are the architecture and the system or the program. So the architecture is the physical makeup. This is the hardware of the agent. This is the box that you have here, and to which the set of sensors and actuators belongs to. So this is the physical object that is linked to the agent, or this is the agent hardware itself. So the program is actually the mind of the agent. This is where the deliberation, the thinking is happening. And this is happening actually here when you get the percept from the sensors, from the physical, but then the agent needs to think about what to do, what would be the word if he does this or that, etc. So we have this really two main components that are not only complementary, they have to be compatible. So the program is limited by the architecture makeup, and we have to really, they have really to be working together in harmony. So basically, you can't, for example, ask your intelligent agent to dance if it's just a simple box on your table. So it would have to be some kind of compatibility between the two pieces. Example of agents include human agents that have as sensors the eyes, the ears, and other organs. The actuators that are the hands, legs, mouth, and other body parts. Robotic agents has as sensors the camera, infrared rangefinders, and other kinds of sensors that allows them to move safely in the environment. And the actuators are the various motors that makes the robot moves. Actually, agents are everywhere. This includes a simple thermostat that maintains the room temperature, to your cell phones that includes a lot of functionality such as emails, web pages, the weather, to the vacuum cleaner that you could program to go around your house to clean your house, to robot that as we said, the Alexa Echo, which is one of the most recent additions that you could add to your house, that can order pizza for you, play your favorite music, maintain your shopping list, switch your lights off, order an Uber car for you, etc. Self-driving car, which is one of the most advanced AI agent that actually is a car driving itself in the street, perceiving its environment in terms of pedestrians, traffic roads, other cars, and acting upon that by moving from one point to another one in the city. And finally, the human agent that actually the most intelligent agent out there. Let's take a very simple example of vacuum cleaner agent that actually evolves in a small environment in which we have two rooms, room A and room B, and potentially some dirt in the rooms to clean up. So the percept of the vacuum cleaner in this environment is the location and the content of the room. For example, if the vacuum cleaner has two sensors, a sensors for dirt and a sensors for location, it could create a percept as a pair, A dirty, for example, is an example to say that, is a percept to say that the room A is dirty. The action that could the vacuum cleaner accomplish are going left, going right, suck the dirt, or do nothing if everything is clean. And finally, we are defining actually an agent function that actually is a mapping between the set of percepts to the set of actions. And this we could write in a table that actually has a mapping between percepts and actions. So for example, if A is clean, then go right. If A is dirty, then suck the dirt. If B is clean, go left and check whether there is dirt afterwards in the left. And if B is dirty, then suck it up. So we're going to, this is a simple actually percept action table pairs in which we have simple percepts, not a sequence of percepts, but just simple percepts on the left and the corresponding actions. So given this, the agent will just need to look up in this table, and depending on what it is perceiving from the environment through its sensors, it will define what it will do. So we could actually make this table longer by not only keeping the percepts single percept by themselves, but having combinations of percepts or sequence of percepts. For example, if A is was dirty, and then A, it became clean, what to do, right? So we're going to can extend this table to not only maintain the percept, but also sequences of percepts. So we are interested in well-behaved agents, and these are rational agents that are defined according to Russell and Norvig as follows. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever background knowledge or built-in knowledge the agent has. So we want this agent to be rational in the sense that it's going to do really its best given what it is observing and given whatever background knowledge the agent has. More specifically, we define rationality relatively to a performance measure, and we judge rationality based on the performance measure that defines the criterion of success, the agent's prior knowledge of the environment, the possible actions that the agent can perform, and finally the agent percept sequence to date. So when we define rational agents, we group these properties under the acronym PEACE, which stands for performance, environment, actuators, and sensors, which is actually the problem specifications for the task environment that the rational agent is meant to solve. So let's define PEACE for some intelligent agents, and let's start with the self-driving car. So for self-driving car, passenger would care about the following performance, which could be the safety of the passenger, its comfort, and also the time to destination. We care also about the legal drive. We don't want a self-driving car that crosses red lights or harms pedestrian. The environment of a self-driving car are all the roads, the other cars, pedestrians, road signs, and so on and so forth. The actuators are everything that makes the car move or interact with the environment, such as the steering, accelerator, brake, signal, horn, etc. And finally, the sensors. The self-driving car is actually embarked with a lot of different sensors. This include a camera, a sonar, a GPS, a speedometer, an odometer, and the keyboard, along with other kinds of sensors that allow the car really to perceive the environment. As a second example, let's take the example of vacuum cleaner. You are probably familiar with the iRobot Roomba series that started about 10 years ago that you could put in your room to clean the floor. The performance of a vacuum cleaner could be measured in terms of cleanness of the room, the efficiency, that is the distance traveled to clean, or the battery life. You care also about the performance in terms of security. You are putting a device in your room that actually has eyes, it has cameras, and it is potentially connected to the Wi-Fi or internet, and you don't want this to be hacked. So security is a very important aspect of this device before you add it to your house. The environment includes anything in the room, such as tables, wood floor, carpets, and different objects. Your kids' Lego could be swallowed by the machine. So the environment is anything around in the room that actually constitute the environment of the room of the vacuum cleaner. Finally, the actuators are actually the hardware of the vacuum that includes the wheels, the different brushes, along with the vacuum extractors to clean the dirt. And finally, the Roomba or the vacuum cleaner includes several sensors. This include the camera, a dirt detector, a cliff sensor. You don't want the Roomba to go down the stairs, fall down the stairs. A bump sensors, because you don't want the Roomba either to ruin all of your furniture, so it has to really detect whenever there is something that the Roomba will will hit. Finally, the sensors include a camera, a dirt detection sensors, a cliff sensor so as the vacuum cleaner doesn't go down the stairs, the bump sensor that allows the vacuum not to bump into all of your furnitures, and finally an infrared wall sensors that allows to detect the size and the limits of the room. So we have seen 2 examples of agents with 2 examples of environment, the street and the room. We could actually categorize environment into different types, and this includes whether the environment is fully observable, in which an agent's sensors give it access to the full picture, that is the complete state of the environment at each point in time. This is versus partially observable, such as the car, the self-driving car, that do not have access, for example, to what's going on 3 blocks away or what's going on behind the truck. An environment is deterministic when the next state of the environment is completely determined by the current state and the action executed by the agent. If the environment is deterministic except for the actions of the other agents, then the environment is called strategic. So basically, a car can't predict the behavior of other cars or the traffic conditions. So the opposite of deterministic is non-deterministic, or what we call stochastic, in which uncertainty about outcomes is modeled or quantified through in terms of probability. So you have this probability of making these actions for the agent. An environment can also be episodic or sequential, in which the agent experience is divided into atomic episodes. Each episode consists of the agent perceiving and then performing a single action. And the choice of action in each episode depends only on the episode itself. The environment is called static versus dynamic if the environment is unchanged while the agent is deliberating or thinking. The environment is called semi-dynamic if the environment itself does not change with the passage of time, but the agent's performance score does. So everything is the same, but the score is going down as the time goes down. This is, for example, the case of chess with a clock. An environment is discrete versus continuous when a limited number of distinct, clearly defined percepts and actions is there. For example, in checkers is an example of discrete environment, while self-driving car evolves a continuous one in terms of both the actions and also the time. A single agent, we talk also about single agent versus multi-agent environment because whenever the agent is by itself or with other agents. We also talk about simple versus multi-agents. In a simple agent, an agent is operating by itself in an environment. There are no other agents operating there. Okay. And finally, known versus unknown, in which the designer of the agent may or may not have knowledge about the environment makeup. If the environment is unknown, then the agent will need to know how it works in order to decide. So this is, for example, the case of a Roomba that you place in a room. So when the designer of the Roomba does not know in which room the Roomba will be put, so the Roomba will be using different kinds of sensors, including an infrared wall sensors, to define what are the limits and the distance in the room. So if we don't know the room, the designer has to embed some intelligence in the agent in order to actually get familiar with the environment in which it will evolve.